Hello everyone, Assalamualaikum warahmatullahi wabarakatuh, and good day to every one of you. So welcome to my video. So basically this is the last video for chapter 1, which is magnetic circuits. Okay, and then in this video we are going to see some example on how to solve the problems on magnetic circuits. Okay, alright, so basically there are three different examples we are going to see, and then we will share with you the solution only for the first two example only. Okay, for the third example I need you guys to go through it and do it by yourself. Okay, so just go to the example number 1. Okay, so refer to this diagram. So you have a ferromagnetic core shown in the figure 1. So three sides of this core are uniform width. Okay, so first side, second side, and third side has a uniform width, while the fourth side, which is here, is somewhat thinner. Okay, so here is thinner compared to 1, 2, and 3. So the depth of the core is 10 cm. Okay, so the depth into the page is 10 cm, and the outer dimension are shown in the figure. So here you have the length is 10 cm, here 30 cm, 15 cm. Okay, so here also 15. Here also 30, here is 15, okay, so here is 15, 30, and 10, and here is 15, okay, alright. So this dimension is very important in order to determine the main length of the core. Okay, so there is a 200 turn coil wrapped around the left side of the core. So here you have a coil with N is equal to 200. Assuming the relative permeability mu r is equal to 2500, how much flux will be produced by a 1 ampere input current? Okay, so this is the question. You need to determine the flux, how many flux will be produced when you apply 1 ampere input current. Okay, so here you apply 1 ampere. Okay, so we just go to the next slide to see the solution for the exam. So from the question, you know that your N turns is given by 200. Your current I is equal to 1 ampere. Okay, so you have three sides of the core with the parameter of width is equal to 15 cm and depth is equal to 10 cm. Okay, so meaning that here you have for this one, so you consider you have that thing. Okay, alright, so here you have 15 cm, okay, and then some sort like that lah. Some sort like this. Okay. Okay, so the depth is equal to 10 cm. Alright. So the thin side of the core. Okay, so this is your thin side. Maybe like this. Okay. So here you have 10 cm, okay, the width 10 cm, and then the depth also 10 cm. Alright, so this is just how I draw it. Okay, sorry for the not a nice drawing. Okay, alright, so your magnetic circuit can be represented by the equivalent electric circuit. Okay, so where you have a magnetomotive force F, and then you have a because you have two different sides, so here we can consider as a reluctance in core 1. Okay, so here we consider as a reluctance of core number 2 because the size, the dimension is different, so that's why the reluctance also can be considered as a different. Alright, so you have two different reluctance value. Okay, so you know that by applying the Ohm's law, you know I will be equal to V divided by R. So in this case, I is a flux, okay, and then your V is equal to magnetomotive force F divided by your R is your reluctance equivalent, okay, and then F will be equal to your N multiplied with I, and then the reluctance equivalent is equal to reluctance number 1 plus reluctance number 2 because it is in series. Alright, and then now you are given the value of N. You know N and then you also know the value of I, but here you need to find the value of reluctance 1 and reluctance 2 first in order to find the value of flux. Okay, so first of all, you need to find the value of reluctance 1. Okay, so you know that the formula of the reluctance 1 will be equal to the length core, the mean length of the core 1, okay, divided by mu 1 multiplied with the cross-sectional area of 1. Okay, so the length number 1 will be equal to, so now you have a red dot here. So the red dot determines the mean core length of the core number 1. Okay, so how to identify the mean core length? So we can just consider this as okay, we can try to from this point to this point. Okay, so you know here is 30 cm. Okay, alright, so from this point to this point, because here is a 10 cm, so you can consider here is 10 divided by 2. Right? Okay, from this point, so here is a 15 cm, so here is a half, so 15 divided by 2. So here also 15 divided by 2. So 15 divided by 2 plus 15 divided by 2 become 15 cm. Alright. So from this point to this point is equal to 30 cm. Okay. Same goes to here. You have a 15 divided by 2. Here 15 divided by 2. So that's why here is 15 cm. Alright. So finally, okay, here you have 30 cm. Okay, so finally here you have 10 divided by 2. Alright, so you can just add on the mean length for the core number 1. So here you have 5 plus 30 plus 15. Okay, plus 30 plus 15 plus 30 plus 5. Right. Okay, so finally the mean length for the core number 1 is equal to 130 cm. Okay, and then you must always remember to change the units from cm into meter first before you can proceed to do the calculation, to avoid the mistakes in doing the calculation. So you can just straight away change the units from cm into meter. So so now you have the mean length for the core number 1 is a 1.3 meter. Okay, and then after that, once you get the value of length, then you can find the value of cross-sectional area of the core number 1. Okay, so the cross-sectional area is equal to the width multiplied with depth. Okay, so for the core number 1, so the width is 15 cm. 15 you convert into meter, becomes 0.15 meter multiplied with 0.1 meter. Here 10, you convert, it becomes 0.1. Okay, so finally you get the cross-sectional area for the core number 1 is 0.015 meter squared. Right, so once you get the value of A and the value of L, then you can just substitute into this equation. Okay, so you get the reluctance of number 1 will be equal to length of number 1, 1.3. Okay, so you have a mu 1 will be equal to the mu naught mu r. Okay, so the mu naught is given by 4 pi multiplied with 10 multiply -7. Okay, so the mu r given in the question is the 2500. Okay, so the A1 is equal to 0.015 meter squared. Right, so once you substitute all the value, then you can get the value of reluctance for core number 1 is 27K 587 ampere turns over Weber. Okay, so this is the first reluctance. Next, we determine the value of reluctance of core number 2. We just repeat the step. So reluctance is equal to the length of the core divided by the permeability multiplied with the cross-sectional area. Okay, so the length for number 2 is given by the blue lines here. Okay, so from here you can, what you can get is, so here is a 15 divided by 2, so which is 7.5, right? And then here also 15 divided by 2, and then from here to here is 30 cm. Okay, so the total mean core length for the core number 2 is equal to 7.5 plus 30 plus 7.5, so you get 45 cm. So you can just change the units into meter, become 0.45 meter. Right, and then after that you just calculate the value of cross-sectional area for the core number 2. The width is 0.1 meter, multiplied with D is 0.1 meter equal to 0.01 meter squared. Okay, so here 10 cm, 10 cm, we convert into meter first. So finally, the reluctance for core number 2 will be equal to, you just substitute the value of the number that you get above into the formula. Then finally you can get the reluctance of core number 2 is equal to 14K 324 ampere turn over Weber. Okay, alright. So once you get the value of reluctance number 1, reluctance number 2, you know the value of N, you know the value of I. Now you can calculate the total of magnetic flux. Okay, so you just substitute the value into the equation. Then finally you got the total flux is equal to 4.77 milliweber. Alright, so this is the final answer. Okay, next we go to the example number 2. So in this diagram, represent the figure number 2, shows a ferromagnetic core whose the mean path length is 40 cm. Okay, so the mean length for the core is 40 cm. There is a small gap. So here you have a small gap of 0.05 cm in the structure of the otherwise whole core. The cross-sectional area of the core is 12 cm squared. Okay, so the cross-sectional area is 12 cm squared. And the relative permeability of the core is 4000. And the coil of wire on the core has 400 turns. So here your N is 400 turns. Assume that the fringing border in the air gap will increase the effective cross-sectional area of the air gap by 5%. So it means here, because you have an air gap here, so the cross-sectional by the air gap might be increased due to the fringing effect. So the size of the cross-sectional area for the air gap is given by 5% of the 12 cm squared. Okay, given this information, you need to find, number 1, the total reluctance of the flux path. Okay, iron plus air gap, meaning that you need to find the reluctance of iron plus the reluctance of air gap. Okay, and then B, you need to find the current that required to produce a flux density of 0.5 Tesla in the air gap. So meaning that you need to find how much I must be required in order to produce a flux density about 0.5 Tesla. So this is your B, right? So the solution to this example is given by here. So you can transform your magnetic circuit into the equivalent electrical circuit such as this, and then because of you have two different material, which is core and the air gap, so that's why you can have the different reluctance value. So the first one is the reluctance for core, the second one is the reluctance for the air gap. Okay, so here you have a magnetomotive force. Okay, and then you have a flux induced along it. Right, so given from the question, N is equal to 400, the B is equal to 0.5 Tesla. Okay, so you know the ferromagnetic core, which is LC, is equal to 40 cm, and your cross-sectional area of the AC is equal to 12 cm squared. Okay, so based on this, you can find the value of reluctance of core. Okay, and then for the air gap, it's given by the length of the mean length of the air gap is equal to 0.05 cm. Okay, and then the cross-sectional area of the air gap is equal to the 5% on top of the 12 cm squared due to the fringing effect. Okay, so based on this, based on the electrical circuit, you can apply the Ohm's law. You know that I will be equal to V divided by R. So in this case, I is the flux, equal to F divided by the total reluctance. Okay, so F equal to N multiplied with I In this case, you don't have you don't have I, but you need to find what is the value of I. So before you can find the value of I, you need to find the value of reluctance of core and the reluctance of the air gap. Okay. Alright. So first of all, you need to find the reluctance of the core. So the reluctance of the core equal to the length of the core divided by mu naught mu r multiply with the cross-sectional area of the core. So just substitute the value accordingly. So in this case, you have 40 cm is equal to 0.4 meter divided by mu naught is given by this. And then the mu r permeability from the question is given you, the value is 4000. Okay. And then for the AC, the cross-sectional area for the core is 12 centimeter squared. So you convert into meter squared, it becomes 0.0012 meter squared. Okay. So after that, you can just use your own calculator. You got the value of reluctance of the core is equal to 66K315 ampere turns over Weber. Alright. Okay. Next, we need to find the value reluctance of the air gap. Okay. So same thing. You know your length of the gap is given by 0.05 centimeter. You need to convert into meter first. And then for the cross-sectional area of the air gap is equal to 5% on top of 12 centimeter squared. Okay, so this is due to the fringing effect. So how to calculate the AG is equal to 1.05 multiplied with 12 centimeter squared. So you got 12.6 centimeter squared. Okay, and then don't forget to change the units into meter squared before you can substitute into this formula. Alright, so your reluctance of the air gap will be equal to this formula. So just substitute accordingly. So in this case, you have 0.05 cm. You convert, you get 0.0005 meter divided by your mu naught. So in this case, because it is an air gap, so it doesn't have the mu r. So that's why it become the mu r is equal to 1. So that's why in this case, mu naught multiplied with the cross-sectional area of the air gap. In this case, you have mu naught mu r multiplied with cross-sectional of the core. Here you have the value of mu r, but here the mu r is considered as a 1 for the air gap. Alright. And then just substitute accordingly the value. Then finally you got the reluctance of the air gap equal to 315K 784 ampere turn over Weber. Okay, so once you find this value and this value, you can just substitute into the equation above. Alright, so we go to the next slide. You know that your flux is given by Ni divided by Rc plus Rg. And then you also know your flux is equal to your B multiplied with your cross-sectional area. In this case, B given by the question is the value of the density for the air. So that's why the cross-sectional area that you are going to use is the cross-sectional for the air gap. Okay, so in this case, B is 0.5 and the cross-sectional area for the A gap is equal to 0.00126. Okay, and then after that you get the value of flux is equal to 0.63 milliweber. Okay, 0.63 milliweber. Once you find the value here, you know this value, you know this value, you know what is the value of N, which is 400. Now you can find the value of I. Okay, so you can just rearrange your equation. You get I will be equal to 0.63 milliweber multiplied with the total of reluctance divided by the number of turn. Okay, so finally you get I will be equal to 0.602 ampere. Okay, so this is the final answer. Alright. Okay. So that's all for the solution for both example 1 and example 2. And then next, let's have a look at example 3. For this example 3, I would like to ask all of you to try to solve this by yourself. Okay. And then we will discuss on the answer on our next class. Okay. Thank you guys. Thank you for your time. Thank you for watching my video. I'll see you in the next video. Alright? Okay, bye.